Hi, my name is Nicholas Dwork. This is the first lecture of Mathematical Foundations of Machine Learning and Computation, and today we're going to be talking about sets. A set is the most fundamental mathematical entity. Its definition, a collection of distinct elements. This is a very fuzzy definition. We're going to use our intuition to understand what a set is, and then we'll see how to work with one. So here's an example of a set. We use the curly braces to denote the elements of a set. This set is named A, capital A, and so A is equal to the set 2, 5, 3. So what can we say about this set? We can say that 2 is in A. That's what this notation with this epsilon means. And we can say that 8 is not in A. That's what this epsilon with the slash through it means. We don't need the same types of elements in a set. Here's another set labeled B, and it has the letter A, the number 18, and the star in it. Here's a special set. It's the empty set. It's the set that has nothing inside of it. And here's an example of an infinite set. It's the set of integers. Order doesn't matter with a set. So the set 5, 2, 3 is the same as the set 2, 5, 3, which is the same as the set 2, 3, 5. The elements of a set must be distinct. So here's notation that looks like it's a set. We're labeling it S, and it has the elements 8, 2, 2, and 1 in it. But since the elements must be distinct, this thing doesn't exist. This is not a valid set. I've shown you two commonly used sets. Here are some more. This fancy R is the set of the real numbers. This is the positive numbers. These are the non-negative numbers. And these are the rational numbers. You can perform operations on sets. We're going to go through some of them now. You can perform the union of two sets, denoted with this large U. It is the set of things that are either in A or in B. So A union B, in this case, is equal to 1, 2, 3, pi 1.2. You can perform the intersection of two sets. It's often denoted with this upside down U. The intersection of A and B are just those elements that are both in A and in B. And in this case, the only element that's in both sets is 3. Often we denote intersection just by putting the set labels next to each other. And so AB is equal to the set containing 3. Let's look at a slightly more interesting example. The intersection of the sets of all real numbers between 0 and 1 and the set of all real numbers between 0.5 and 10. And that equals the set of all real numbers between 0.5 and 1. So you could perform intersection with infinite sets. Another operation on sets is the complement, denoted with either a bar or a superscript C. It is the set of all the elements that are not in A. Let's talk about such that notation. Here's an example of an interval, all real numbers between 0 and 1. Here's a more concise way to write that. And so the way you read this is all real numbers x such that 0 is less than x is less than 1. So here's our example from before. Now you can see that we can write it more concisely, like so. We could compare sets. Let's talk about some comparisons. This is read A is a subset of B, and what it means is that all elements of A are also in B. This is read A is a superset of B, and it means all elements of B are in A. This is the equals comparison. It's read A equals B, and it means that A and B have the same elements. Equivalently, it means that A is a subset of B, and B is a subset of A. A common way of proving that two sets are equal is to show that each is a subset of the other. And we're going to do an example now. A is going to be the set of integers n such that n is even, and B is going to be the set of integers n such that n squared is even. And the question is, are these different sets or are they the same? Before we go about proving that, let's discuss some symbols. Any proof should be written in complete sentences, including punctuation. And the goal of a proof is to be clear and convincing. So we often use mathematical symbols to make the proof shorter or more concise, but we should always be able to replace those symbols with their meaning and get complete sentences out. Here are some symbols. This backwards capital E means there exists. These 3 dots means therefore. The upside down A means for all. The square means end of proof. This right arrow means implies. The double right arrow means if and only if. And arrows pointing at each other means there's a contradiction. Okay, so now we're going to prove that these two sets are indeed equal. First, I claim that A is a subset of B. So let X be an element of A, then there exists an integer k such that X is equal to 2k. Why? Because A is the set of even integers, so if X is even, then it must have a factor of 2. If we square X, we get 2k squared, which is equal to 4k squared, which is equal to 2 times 2k squared. 2 is a factor of X squared. Therefore, X squared is even. Therefore, any element in A is also an element of B. Therefore, A is a subset of B. Okay, now I claim that A is a superset of B. Let's suppose that A is not a superset of B. Then there exists an X in B where X is not in A. This implies that there exists integer k such that X is odd. X is equal to 2 times some integer plus 1. That is, it is an even number plus 1. Let's square X. X squared ends up equaling 4k squared plus 4k plus 1. Factor out a 2 just out of the first two terms. That equals 2 times the quantity 2k squared plus 2k quantity plus 1. Okay, so X squared is now an even integer plus 1. That means that X squared is odd. But then that's a contradiction because X squared is no longer in B, whereas we said X was in B before. Since we arrived at a contradiction, our supposition is false, the opposite of our supposition must be true, and therefore A is a superset of B. Okay, since A is a subset of B and A is a superset of B, A equals B. End of proof. We can have ordered sets. We denote them with the parentheses. So here's an example of an ordered set, 1, 2, 5. And this does not equal the ordered set 1, 5, 2. These are now different sets because order matters. So we only had sets. Where did ordered sets come from? I'm going to show you now how to construct ordered sets using sets. Here's an example. The ordered set is 1 pi 8. How do we have a set that defines this ordered set? Well, it's the set on the right. It's the set of 3 sets. The first set just contains 1. The second set contains 1 and pi. And the third set contains 1 pi and 8. Okay, so if we want to know the first element, we just look for the set that only has 1 element in it. We look at the element in that set, and that's the first element of our ordered set. Great. What if we want the second element? We look for the set in our ordered set that has 2 elements in it, and we look for the element that's never been seen before. We've seen 1 before, we haven't seen pi, therefore pi is the second element. Similarly, if we want to know the third element, we look for the set that has 3 elements in it. We look for the element that's never been seen before, that's 8, and therefore 8 is the third element. So ordered sets are actually defined as sets. No one really thinks about it like that. We always just think directly about the ordered sets, but it's good to know that they're defined using sets in the background. Here's another example of an ordered set, all the integers larger than or equal to 3, and this is an infinitely sized ordered set. Here are other examples of sets. These are intervals. The square brackets means inclusive, the parentheses means exclusive, so square bracket AB is equal to the set of real numbers x such that A is less than or equal to x is less than or equal to B. The parentheses A comma B is equal to the set of real numbers x such that A is less than x is less than B, and you can mix them. So here's our example from before, and now you see using intervals we can make this even more concise. It's the set of intervals 0, 1, intersection 0.5, 10, and that equals the interval 0.5, 10, non-inclusive. Now we arrive at an unfortunate ambiguity. What is parentheses 1, 2? Well, it can either be the ordered pair 1, 2, or it can be the interval from 1 to 2. And so if you write this, you either have to make sure that it's disambiguated by the context, or you have to explicitly say what you mean. Here I'm defining the Cartesian cross product. Consider sets script x and script y. The Cartesian cross product of script x with script y is the set of ordered pairs x and y, such that x is in script x and y is in script y. So here's an example. R2 is a set of ordered pairs x and y such that x is a real number and y is a real number. You can see why this is considered R2 because it is the Cartesian cross product of R with itself. More generally, you can have Rn, which is the Cartesian cross product of the real numbers with itself n times. Let's talk about line segments. So let x and y both be elements of Rn. The line segment connecting x and y is the set of 1 minus gamma times x plus gamma times y, such that gamma is in the interval 0 and 1 inclusive. Okay, so why is this the case? Well, let's think about R2 as an example. So both x and y are represented by ordered pairs. And since they're represented by ordered pairs, we could draw them on a graph. So maybe this point in the upper left is x, and maybe this point in the lower right is y. Okay? Well, what happens when gamma is 0? Then 1 minus 0 is just equal to 1 times x plus 0 times y, so that equals x. Okay, so when gamma is equal to 0, we start at x. Well, what happens when gamma is equal to 1? Well, then we get 1 minus 1, which is 0 times x, plus 1 times y, which equals y. Okay, so then when gamma equals 0, we're at x, and when gamma equals 1, we're at y, and when gamma is between 0 and 1, we get the line segment in between them. We're going to learn to love convex sets in this class. It's going to play a major role, so let's talk about what that is. A set is convex means that the line segment connecting any 2 points in the set is also in the set. Okay, so here are some examples. This is a set, it's in R2. I can choose any 2 points in the set and draw the line between them, and the line lies entirely in the set. Okay, so this set is convex. Here's another set. I can take 2 points in this set, and the line connecting them does not lie in the set. Therefore, this is not a convex set. And these sets don't have to be bounded. Here's an example of a set. You can imagine these lines going up forever, and this is a convex set. You can take any 2 points and draw the line between them in the set, and sure enough, the line will always be within the set. So this set's convex. Formally, a set C is convex means that for all x and y in C, the line segment connecting x and y is a subset of C. Okay, that does it for today. Thank you for your attention.